This lecture is part of an online course of multivariable calculus, and I'm going to talk about parametric surfaces. So assume that we have a surface S in R3, something like sphere or cone or cylinder, but something more general than those. And then we can use two parameters to parameterize that surface. I'm going to show it the parametrization by R of U and V, and I can say that this parametric equation for the surface S has coordinates x, y, and z, where x is a function of two parameters u and v, y is a function of u and v, and then z is a function of u and v. Okay, where u and v, they are in the region D. D is a region in R2. So D is a region in UV plane. Okay, so let me give you a recall. And if you remember, when we have a curve in a space, in R3 that we show it by C, we use just one parameter t to parameterize that, R of t, and we said that our curve C has coordinates x of t, y of t, and then z of t, okay, where t is in one interval a and b in R1. Just basically real numbers. Okay, so curve has just 1 degree of freedom, so that's why we just use one parameter to parameterize a curve, because it's just basically we just need one parameter to parameterize that. But for a surface we need two parameters, u and v. We need two parameters because we have 2 degrees of freedom. That's why we use two parameters for parameterize a surface, but for a curve we just need one parameter. And then the parameter is on an interval in R, but here two parameters is in a region in R2. Okay, let's look at some important parameterizations and then see how we can parameterize those surfaces. Okay, so this is the general formula, and then important parameterizations. Number one, if we have graph of a function z equals to f of x and y. Okay, if I want to parameterize that, I can say that I'm gonna let x to be my u, my first parameter, y to be v, and then z would be f of u and v. Okay, so the parameterization that I'm gonna use in here would be s, it's r of u and v. The first coordinate is u, the second coordinate is v, and the third coordinate is f of u and v, where u and v are in the domain of the function f. Okay, so this is kind of like a general notation that we're going to use. Look at, for example, sphere. I'm going to use sphere of radius, for example 5, centered at the origin. Okay, so equation of that is this: x squared plus y squared plus z squared equals to 5 squared. Okay, so let me show it to you. The sphere, that's the sphere x squared plus y squared plus z squared equals to 25, x-axis, y-axis, and then z-axis. Okay, so how can we parameterize that? I'm going to use spherical coordinates to parameterize it. And if you remember that we talked about spherical coordinates before, let me just graph the sphere also in here. So I have, oops, x-axis, y-axis, and then z-axis. I have the sphere. Let me just move it a little bit. And then on the spherical coordinate, rho would be the distance from the origin to the surface of the sphere, and rho here is 5. Then I have phi, and phi is the angle to the positive z-axis, so phi could be from 0 to pi. And then I have theta. Theta is like polar coordinate, which is basically I'm gonna have the projection of this row on the xy plane, and then I have theta, which is the angle to the positive x-axis actually. So oops, let me change it. So this is theta. So when I want to parameterize that, I get 5 and then sine phi cosine theta. For y, I have 5 because the radius of the sphere is 5, and then sine phi sine theta, and then z is equal to 5 cosine phi. Okay, so as you see, I have two parameters, phi and theta, to parameterize my sphere, and then phi is between 0 and pi, and theta is between 0 and 2 pi. Okay, so the parameterization for the sphere that I have in here has two parameters, phi and theta, and then I have x coordinate, y coordinate, and z coordinate. For the general sphere of radius a, for any sphere of radius a, I can write a in here, and then sine phi cosine theta, and then a sine phi sine theta, and then a cosine phi, where phi is between 0 and pi, theta is between 0 and 2 pi, and then this is parameterization of x squared plus y squared plus z squared equals to a squared. When a is equal to 5, I get this one. Okay, very good. Now let's look at the next example, which would be parameterization of a plane. So let's look at one plane, 5y plus 7z equals to 10. It's a plane. Okay, let me show you to you the graph of this plane. It's right there. Okay, you see x-axis, y-axis, and z-axis, and then I have this plane in here. For parameterization of the plane, I'm gonna let x to be my first parameter, y to be my second parameter, and then z would be a function of x and y. So let's isolate z from here. So 7z is equal to 10 minus 3x minus 5y. So z would be 10 minus 3u minus 5v divided by 7. Okay, where u and v are both of them in R2 is just because it's just the plane. Okay, so the parameterization that I introduced in here would be u, v, and 10 minus 3u minus 5v divided by 7. This is basically an example for the general case that we talked about in here, that when you have z as a function of x and y, let x to be one of them, y to be the other one, and then write z. Okay, let's look at example 4, parametrization of a cylinder. Let's take x squared plus y squared equals to 5 squared, where z is between, for example, 2 or negative 2 or to 2, for example. It's a cylinder. Okay, let me show you to the graph of this cylinder. It's a cylinder. As you see, the cylinder since has the equation of a circle in the xy plane and z is free, that's why this cylinder moves, it's free on the z-axis, so it runs along the z-axis, as you see in here. Okay, so how can we parameterize that? Well, I'm gonna use basically something like a polar coordinate for it, but here 5 would be fixed because the radius of the cylinder is fixed. So I'm gonna say x to be 5 cosine theta, y to be 5 sine theta, and then let z to be my second parameter. Z it's just basically cylindrical coordinate that looks like polar coordinate in R2. And then I'm gonna say theta between 0 and 2 pi, and then z between negative 2 and 2. So for the general cylinder, the parameterization that I'm gonna use would be this. Would be a cosine theta, and then a sine theta, and then z would be my second parameter. So the parameters would be theta and z, and the a here is just the radius of the cylinder in general. X squared plus y squared equals to a squared. This is constant. This is not parameter. Parameter would be the angle and the axis, z-axis. Okay, and then look at the last example that I want to say. Z squared equals to x squared plus y squared. It's a cone. Okay, let me show it to you, the graph of the cone. There you go. That's this cone. Z squared equals to x squared plus y squared, and I want to parameterize that. So how do I do it? Well, you see, for the cone, I'm gonna let z to be my first parameter u, and then if z is equal to u, I have a circle of radius u, as you see in here, if z is equal to u. Then I'm gonna use polar. So a circle of radius u, x would be u cosine theta, and y to be u sine theta, and then theta is between 0 and 2 pi to make it full, and then z is in r. Okay, so r of u and theta here would be what? Would be u cosine theta, u sine theta, and then u. Now you just compared cylinder with the cone. On cylinder, we don't have a parameter. We don't have two parameters on the coordinates. We just have one parameter here for example, x. X is just function of just one variable. A is just the number is constant. But for the cone, X coordinate and Y coordinate, these are functions of two parameters, two variables, u and theta. U is changing, theta is changing. For the cylinder, the radius is fixed, and then the angle is changing. For the cone, the radius is also changing. Okay, very good. These are the most important parameterizations, and that's it.